we completed the rotational spectra, vibrational spectra. Then we discussed different cases for both in a diatomic molecule. And there is electronic spectra actually. We have almost done electronic spectra. The condition, the physics is same for an atom and a molecule, and the atomic physics part. But there we have the atomic energy levels. Here we have a molecular energy level actually, and there are different atomic electronic spectra of these molecules. Different techniques are there, like X-ray photoelectron spectroscopy is one of them. We will not go into detail it this time. And before that, electronic spectroscopy or electronic spectra, we will just see one of the practical examples of these spectra, which can be seen, and that is what we call as Raman spectroscopy. Raman spectra. So you almost, I think you might have gone through the basics of the Raman spectra, and if not, so it is a simplest thing, simplest one, but it is a very important from the physics point of view. And Raman spectroscopy is actually a spectroscopic technique which was discovered by Raman actually in this 20th century in 1959 or something like that. I don't know the exact date. What he observed is that he observed that if we have a beam of light, when it is passed through a medium, so the medium has molecules, any medium, whether it's a transparent, it is a translucent, it is a organic, it is a gas, it is a liquid, or it is a solid as well. And mostly liquids and gases can be used because solids have very high binding energies and the cohesive energies. So when a beam of light is passed through a medium, so when we pass it through a medium, there may be different processes which may be going on. There may be a diffraction, there may be scattering, there may be absorption, there is emission. We all know that this all happens whenever a beam of light, that means a photon is passed through a medium. So what we are concerned here is scattering. Scattering of the beam of light by the molecules of the medium. And that too, in this scattering, we have elastic, we have inelastic. When it is elastic scattering, that means the frequency with which the photon strikes the molecule. This photon is emitted back with the same frequency. There is no loss of the energy. Then it becomes elastic. And such elastic scattering, this type of elastic scattering is called as Rayleigh scattering. And this inelastic scattering, this is what we call as Raman scattering.
Sir, repeat.
Okay. So that means whenever there is a collision between a photon and a molecule in any medium, this photon can be scattered. It can be scattered with the same frequency, that means the frequency with which it was coming, or it can be scattered with different frequencies, maybe less than or greater than the initial frequency. Okay, so when it is same frequency, that it is called as Rayleigh scattering. That means same energy. Okay, we'll go into a more detailed picture, but here just understand that, just remember that whenever the scattering is elastic, it is called a Rayleigh scattering. And when it is inelastic scattering, that means the scattering of a beam of light by the molecules, the inelastic scattering, is actually called as a Raman scattering or Raman phenomena. Simply, the Raman scattering. Okay. Now, this inelastic scattering, it has two conditions, two possibilities. So, if we assume that the incident photon has energy h nu, E, it is E incident, and it is scattered. Scattered means you know how the scattering happens actually. It goes into some ground state, it excites an electron to the another molecular level, then comes back and emits that energy. Okay, that's how the scattering happens actually, which is emission actually. So incident is h nu, and this h nu will, if this h nu is exactly equal to these two energy levels, suppose that there is a transition from this ground state level to excited state, and the change this energy level, it is delta E. Okay, and when this delta is, and we have an emission of, there is a h nu, this h nu should be at minimum at least equal to delta E, so that it can make a transition. It can knock out an electron from here, so it will go to the higher molecular energy level. Then it comes back to the ground state and it emits this energy of the same frequency, of the same energy. Okay, and then it is called Rayleigh scattering. But in the case of Raman scattering, it may be it is inelastic scattering. It is not the elastic one. It is not the Rayleigh. It is Raman. So the difference between these two is that in Rayleigh we have elastic scattering, in Raman we have inelastic scattering. And these frequencies, for example, if we draw the spectra like this is a Rayleigh line. That means this is a line we observe of the same frequency, which is the incident light. That means we are shining some light of, this is the line which is observed in the spectra, and it has the same energy and frequency as that of incident. So this will be Rayleigh. There may be some lines, there may be some lines, there are some scattering actually, spectral lines, spectroscopy. In this Raman spectra, we obtained some spectral lines whose frequency here maybe, this is the intensity. Remember that the length of this line will represent the intensity, not the frequency or the energy. Here, that means the frequency of these lines or the energy of these lines is greater than the incident light. That means this change, what I can write is that if molecule, I will write again here, I will write in this way. Let us just focus here. If molecule gains energy, remember that. If molecule gains energy, delta E, that means this much, for example, so it is absorbed. Then the photon, this h nu photon, it will be scattered here somewhere by the energy or the frequency. I can write h nu minus delta E. Is it okay?
No, sir, repeat.
So what I am saying is that, for example, this transition needs an energy delta E to take place. If molecule gains this much of energy and photon is coming with some energy h nu, do you understand? Is it okay up to here?
Yes, sir.
Then the photon, coming photon, it will be scattered at the energy h nu minus delta E. Try to understand. If h nu is exactly equal to delta E, if h nu is exactly equal to delta E, this is change
Delta.
actually. This is change in energy. The change in energy of the incoming photon when it is scattered. So if it is exactly equal to this much, their change is zero. There is no change. When there is no change, there will be a scattered photon with the same energy, which is the Rayleigh scattering. There is no change. I am talking of the change in the energy. Now, if molecule absorbs energy, if it gains some energy, this delta E, delta H nu can be greater than delta E or less than delta E. Sorry, delta E can be greater than H nu or less than H nu. That we will see. So if molecule gains energy delta E, this photon will be scattered at H nu minus delta E. What will the frequency of this photon? That will be it be nu dash. Sorry, nu minus. Now, if molecule loses energy, delta E, molecule is gaining energy. Where from it will gain? It will gain from photon. It will be subtracted. Molecule loses energy. When molecule loses energy to what? It will lose to photon.
Mhm.
There are only two bodies, photon and the molecule. So molecule will gain energy from what? Photon. So photon will lose energy. When molecule loses energy to what? It will lose to photon. So photon will gain now energy. These are two statements, but different aspects, two opposite aspects. Then the photon will be scattered. The scattering frequency will be nu plus delta E by H. This is our scattered photon because the scattering will be measured of the photons. We are measuring the scattering of photons here. Now don't confuse yourself. These are two different ways of understanding the two different actually phenomena which occur during a Raman spectroscopy. Raman phenomena, Raman spectroscopic phenomena. So molecule can gain energy from the photon which is coming to the molecule in striking to the molecule. Molecule lose energy to the photon. Okay, when molecule loses energy to delta E, gaining, you understand, that means it excites some electron, goes to some energy level, and it comes back. It is losing energy. Molecule is gaining energy in that way. Like here. Okay. So gaining is, you understand how it happens. Simple. By loss, what we mean, we have some electron energy levels. We have different ground levels, energy levels in the ground state. You are exciting a molecule here. This is the delta E. Sorry, this is the from ground to bottom. This is excited. Suppose that if molecule is already in some excited state, if molecule is already in some excited state, for example, molecule was having in this state already in some higher excited state, higher order state, and we are incident the energy which is greater than this interval. Let us suppose that this is delta E dash and this interval is delta E double prime. We are making a incidence of radiation h nu, which is greater than or equal to delta E double prime. But our molecule is in this state. So what will happen? It will be excited to this state, but it can come back to this state here. When it comes back, this photon, which is coming here, it will have higher energy as compared to this, or the incident energy. Try to understand. That means when a molecule is already in some excited state, okay, when it goes to some another higher energy, it comes back. There are different possibilities for a molecule to be. You know that a molecule, when it is at rest equilibrium, it is not completely in its equilibrium. It is not a completely a rigid rotor. It is a non-rigid one. We have already stated that. There are some vibrations going on at the equilibrium. There is a vibrational energy state. If you remember this curve, nu equal to 0. Even at the ground state, it has some energy, vibrational energy. Okay, it has some rotational energy. So that means it has some already some higher energies. It is not completely at rest. It has not completely a zero energy. So that energy makes it possible to have that molecule that can make it possible that it may be in some higher excited state. And the energy which we are incident, it is equal to that state, or it is less than or equal to greater than that state, but in the final outcome it can go even to a lower state. It was from here going to this state, coming back to this state, means that the incident photon has energy greater than this. That is what this nu plus delta E by h means. Okay. So there is a possibility molecule can be in any state, depends upon its energies, what type of energies it have. So these two cases can be concluded that during Raman scattering or inelastic scattering, the scattering of the light or the photons results in that change in the energy, where the scattering of these photons that results in that the change in the energy occurs by two ways. Either a molecule can gain energy from the photon, or molecule can lose energy to the photon. Lose energy to the photon means that it was already in some excited state, that much of energy is lost to photon by because it was already in the excited state. So excited state, it was at some higher energy. So when it was at some higher energy, that higher energy part by which it was, by the amount it was at the excited state, that part will be lost to the scattering photon. So scattering photon gains energy. So you have the frequency which is more than the incident frequency. And that is what I draw here actually, in this case here. This. And when the molecule gains energy, it absorbs this, it can have the energies here. Okay, so this is, if we have initial frequency nu naught, this will be nu, this is nu naught minus nu. Okay, or this can be written as nu naught plus delta E by h. This is nu naught minus delta E by h. These lines with the frequency, when your These are called Stokes lines, anti-Stokes lines. So in Raman spectra, we can have Stokes lines where the frequency of the scattered light is less than the incident frequency. We can have anti-Stokes lines where the frequency of the scattered light is photons or scattered photons, a beam of particles is greater than the incident frequency. These will be called as anti-Stokes lines. So the intensity goes on decreasing as you move different energy levels as a transition takes place at a particular given frequency. Remember that we will be using monochromatic energy source. We will use monochromatic energy source so that these transitions will be sharp. You will obtain sharp lines. Otherwise, there will be a continuous spectra. You will not be observed to identify the features of the spectra. So Raman spectra can be observed by the molecules which can have both either vibrational or rotational spectra. So they can have a rotational spectra or the vibrational spectra, because scattering or the transitions which take place when the photon strikes the molecule, they come in the range of these vibrational energies or the rotational energy, or sometimes the both, because I already told whenever there is a vibration there is a rotational energy, this transition which is accompanied with it, that will be there. Now what happens actually when the atom or molecule absorbs the photons? What is the physical quantity which is changing there, which is affected? You know that if we have a molecule, for example hydrogen molecule, this is hydrogen atom, there's another hydrogen atom here, okay, this is a bond between the hydrogen atoms, there is a positive nucleus here, there's a negative electron, so they two are these two electron nucleus, so there's a dipole moment, and there's a dipole moment which is associated with this molecule. Whenever you apply some photon, when a photon is incident on this molecule, a photon is actually an electromagnetic wave, it has a wave nature, so that electromagnetic wave has an electric field vector. That electromagnetic wave, or that means a photon is actually an electromagnetic wave, and that photon has actually an electric field component. So that electric field has its own dipole moment that will interact with this. The incident photon has an electric field. That electric field will interact with this dipole moment, because it's a positive, there's a negative, positive, negative. The charge separation is there. So this external field, now you treat just a dipole in external field. You are treating the dipole in the external electric field. So what will this electric field do? This will induce dipole moment in it. There will be induced dipole moment in the molecule, and that induced dipole moment mu will directly proportional to the strength of the field. This all you have done. I expect and I know that you might have done it, must have done it. Or this mu is equal to alpha E, induced dipole moment. What is alpha? Because a torque will be applied on those charges, which will be, it will shift actually, not the torque, general the electric field strength. Okay, so there will be this electric field direction. It will be from positive to negative. So these negative will repel these electrons, this positive will repel this positive. So there will be some separation between the charges. Then that is what we call as polarization. So the external field polarizes the molecule, or the molecule is said to be polarized. The magnitude of that induced dipole moment, it depends upon the applied field strength. And this is what the simplest expression, which is the basic cause of the Raman spectra. That means if there is a change in the polarizability, then that molecule is said to be Raman active. The basic parameter, basic condition for the Raman spectra to take place in some molecule is that molecule there should be a change in the polarizability of that molecule when some external radiation is incident on that molecule. That external energy must change its polarizability or the induced dipole moment. Simply the polarizability is here main factor. And remember that this polarizability is a tensor, and it is an property which varies along different directions. Why? Because the direction of positive and negative charges, the direction in which they are, there will be polarization. The direction in which they are, there will be a polarization. If not, in direction in which there is no charge, there is no polarization. So it is a direction dependent. In a particular direction, there will be more polarization, but in some particular other direction, there will be no polarization. For example, this case here, there will be a polarization. This applied field, it will try to mark them, but not in this direction. If we have a hydrogen molecule like this, here is minus charge. Okay, for example, here is a positive nucleus. So you are applying field here. So the polarization will be in this direction. So it is an anisotropic. The polarizability is said to be anisotropic. Anisotropic means that if if the polarizability changes along different directions. So this was basics about the Raman spectra, and it is important that whenever we want to study the Raman spectroscopy, the polarizability is the important factor. And this polarizability of a molecule in different directions, polarizability, that's actually the measure of the polarization, the property which is associated with a molecule that it can be polarized. So the polarizability of a molecule in different directions, actually it is represented or it is shown by drawing a that is called as polarizability ellipsoid. So what is exactly polarizability ellipsoid? It is just a representation actually, because it's a direction dependent. That is why this drawing is important, and this drawing gives you the idea in which direction the polarizability is important, if the polarizability is, and what is the magnitude of that polarizability. The polarizability ellipsoid actually for any molecule which is subjected to external radiation is a actually three-dimensional surface. It's a three-dimensional surface. In this three-dimensional surface, the surface is drawn with respect to a center, and that center is called as electrical center. Electric center. You have a center of mass, center of gravity. Okay. So similarly, we have electric center. So center of mass, where we assume that the total mass should be uh, this will be present. Similarly, the total gravitational force, while they will act on the center of gravity, the that moment of inertia axis. Similarly, we have an electric center where we assume that the total charge of the atom molecule may be present. Okay, so it is a surface which is drawn with respect to this electric center. But the condition is that how you will draw that, what parameter you should keep in mind. So from this electric center, the distance is always proportional from this electric center. That distance is always proportional to 1 by under root of AI. And what is AI? AI is actually, for example, if I draw, this is a polarizability ellipsoid, and the molecule is in this, like this, we have molecule, and here somewhere there is an electric center. Okay, from this electric center, the polarization will be different here, polarizability will be different here, polarizability will be different here, polarizability will be different here, it will be different, and it will be different here. But the condition is that everywhere it is proportional to 1 by under root AI. This is A polarizability. This is a polarizability at the point I on the ellipsoid surface. This is ith point here. 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 This is the ith point here. So everywhere the relation is same. One by under root AI. So the polarizability ellipsoid, I will define it again, is defined as a three-dimensional surface whose distance from the electric center of the molecule is proportional to 1 by under root AI, and AI is polarizability along the line which join as a point I on the ellipsoid with the electric center. So remember that wherever the polarizability is large, the ellipsoid will have least dimension. That means it is inversely proportional. So if polarizability is large here, because you are applying electric field here, this is along the minor axis of the ellipse, and along this direction there will be no polarizability. I will take 10 minutes maximum, 10-15 minutes, I will finish it, don't worry. Just try to understand. If you are not able to understand, let me know, I will repeat it. So that means the direction in which the polarization occurs is the least distance from the electric center. So here, okay, and so along the minor axis of the ellipse, the polarization is maximum, so it is inversely proportional, and along the major axis, the polarization is minimum, just like the moment of inertia. The momental ellipsoid, that is called a momentum ellipsoid. So these are the basic definitions. Now, if we take different molecules, any molecule, for example, let us take a hydrogen molecule, which I have already taken. This is hydrogen atom. For example, this molecule has a rotation. We have already studied what types of rotations can be there. There can be along the bond axis. There can be end-over-end rotations. They may be parallel to the plane of paper or perpendicular to the plane of paper. And we also know that the change in the polarizability is must for the molecule to show the Raman spectra. Change in the polarizability is must. And when there will be a change in the polarizability? When there's a change in the centers of the positive and the negative charge. There will be change in the electrical center. When there is some radiation which is incident upon the molecule. When there is a change between the positive and the negative electrical center or positive and negative charge, there is a change in the size of the molecule. There is a change in the size of the molecule. So whenever the size of the molecule changes, that means there should be a change in the bond axis. So whenever the bond axis it shrinks or it expands, there will be change in polarizability. And then there will be the molecule will be Raman active. So if you, this is a hydrogen atom and there are different rotations, there will be a vibration as well. Vibration spectra can also lead to the Raman spectra. In the rotational case, there will be end-to-end rotation, there will be end rotation along the bond axis. So let us first take the bond axis. So whenever the molecule rotates about the bond axis, there will be actually same electric field at all orientations. That is, its polarizability will be exactly the same in any direction across the axis. In any direction across the axis. Just remember, I am going here. Whether you go when it moves at any point in this case. Okay, so if it is a polarizability ellipse, sorry, here this is the axis. Okay, so here there will be the polarizability in this area when you apply the electric field. So along this axis, any direction here, because it is an ellipse, so remember that it is a 3-dimensional. So from this center at out of the paper perpendicular to the plane of paper or into the plane of paper or along the this bond axis, it will be same, and there will be no change in the polarizability. So if you want to draw this ellipsoid, how you will draw it? For hydrogen molecule, here it is drawn actually, yes. So H, this will be, there will be another one here. So there will be different ellipses in different direction, but along the bond axis they all will be same, and they will be then circular. So now in the rotational case, if we have a molecule whose rotational quantum number is J and energy is Ej, then you know that Ej will be equal to B J into J plus 1 when taking centrifugal distortion. This is the expression. If we take D equal to 0, that means we are taking the rigid molecule, no centrifugal distortion, Ej will be equal to B J equal to 0, 1, 2, this. And remember that the selection rules for the pure rotational spectra where delta J is plus minus 1. But remember that here in the Raman spectra, it is not plus minus 1, it is 0 and plus minus 2. This is the important case. The selection rule for the Raman spectra, that is pure rotational Raman spectra, is plus minus 2. And why it is plus minus 2? Remember that when there is a rotation about the bond axis, the molecule changes its position 2 times. The rotational quantum number changes by 2 units rather than the 1 with the symmetry of the polarizability ellipsoid. That means a molecule here, when it rotates by 180 degree, it will shift it will change its J by 1 unit. When it rotates another to retain its original position, it will change its J by another 1. So the total change will be plus 2. And generally plus 2 is taken, not the minus 2, because it is taken as J of upper state minus J of lower state. That is a rule, conventional, like sign convention. So when you take delta J is plus minus 2, then delta E between two rotational levels during the Raman spectra. This is during Raman spectra. Is EJ dash, which is the higher level. It is J plus 2 minus EJ prime equal to J. That means from J to J plus 2. So J changes by plus 2. And when you put up here, you will find that delta E will be equal to B into 4J plus 6. Okay, this is the expression for the interspacing between the two energy levels. Now, when a molecule gains the energy from external photon during collision, what happens? There will be a Stokes line or an anti-Stokes line. The wave number corresponding to some series, because we have already seen the series, there will be a Stokes S or any Raman series. Let us remove this. It will be V external, that means the Rayleigh line, plus minus delta E, which we have calculated here. And I can write it as so the allowed transitions will be only those that will follow delta J equal to plus minus 2. So in pure rotational case, it is important to remember that the intensity of the Stokes and the anti-Stokes lines, they are almost comparable in pure rotational spectra, but in vibrational or vibration rotation, it changes. So how will you draw the spectra condition की problem आता है? So here it is by plus 2. And the series which you will obtain similar, there will be different series actually, and the separation between these, this for J equal to 0, J equal to 2, J equal to 4, J equal to 6, because it is changed by plus 2. So when you put up those values, We'll find that this is 6b with respect to the origin. This is new external here, and between these two lines, this is 4b. Try to find out when j is equal to 0 and j equal to 2, or when j equal to 2 and j equal to 4. Just try to find out this distance. This is important. You will find that it will be 4b between the two lines of the same series, that is Stokes lines or anti-Stokes lines. So these are Stokes. These are anti-Stokes. Okay. So this was a case for rotational Raman spectra. So what happens when we have vibrations in the molecule? So it is vibrational Raman spectra. We already know that there should be a change in the polarizability for the Raman active molecule, so that we have a Raman spectra. So either we can change the polarizability by rotations, and that can be done also by the vibrations. Let's take a simple example of the carbon dioxide molecule. Any molecule, and or H2O molecule, water molecule. You have to see that if the given molecule is Raman active or not. For example, if we have a molecule, any molecule, let it be water molecule, O, H, H, it will undergo vibrations. We already know that there are two types of those rotations, end over end rotations and bond axes along the bond axis. Similarly, we have vibrations, different types of vibration, and these are generally three. Each type of vibration or each particular vibration is called a mode. Each vibration is called a mode actually. So vibration can be stretching, it can be bending. Okay, so we can have a symmetric stretching, we can have asymmetric stretching, and we can have simply bending. This is the simplest case. Now we have symmetric stretching mode, we have bending mode, asymmetric stretching mode. These three are there. Now how they will contribute to the Raman spectra, and how they will change the polarizability, and hence the ellipsoid, polarizability ellipsoid. Now see here, there is a molecule O, it has OH2 here, H, they have 120-degree angle, bond angle. This is a double bond. This is O here, this is H. The symmetric stretching mode, that means it can vibrate along the bond axis. This is one way of vibration. Another way of vibration is sorry. can go. Okay. Now see here. Either the molecule, these hydrogen atoms can move away from the oxygen at the same time. Same time. That means this H goes here, this H goes here, this O can go up. Okay. This is one way of stretching. They can also come close to each other. If, for example, there were some initial equilibrium position here, this is the equilibrium position initially, then there was a radiation which made it to stretch or to vibrate. So it can vibrate, either both atoms go like this keeps here, this remains here, or they can go like this, come close towards oxygen. This vibration will be a symmetric vibration, symmetric stretching mode, and it is represented by nu1 everywhere in any molecule. Okay, symmetric stretching. Now what is bending? You know that how we bend molecules, how molecules bend. This is O, this is H, this is the initial position. So either this H goes up, this H goes up, or down. H goes up. It is just like you are standing, your hands are down, you take your hands up, so you are bending your hands upwards. Okay, then with respect to hydrogen, the head is down, the O is down, this is bending. Okay, or the another way is that your hands are up or they are in the air, you move them down, and with respect to hands, your head is up. So that can happen like this: O, H, H. Okay, this is down, both are down. This is the bending mode, and it is represented by nu2. In the third case, which is asymmetric, asymmetric means that this is oxygen, this is hydrogen, this is hydrogen. If this is the equilibrium position, start from some equilibrium position, and the asymmetric stretching is, this is a one hydrogen comes close to this, one moves away. Now this hydrogen comes close, this moves away. This is asymmetric stretching mode, and it is represented by nu3. So based upon these vibrations, you have to check if the molecule has any change in the polarizability, because size of the molecule will change. Okay, and it depends if the molecule is linear or if the molecule is non-linear. That will also determine its change in polarizability. The simplest example I will give you, and see, we will see that polarizability. Let's take a linear example: carbon dioxide. C, O, this is the last one. Oh, I will leave you after this. Now let's suppose this is its equilibrium position. It's a linear molecule. What is a non-linear with 120-degree bond angle, and this is a linear. This is the symmetric. Okay, this is the equilibrium position. Let us suppose that it is the equilibrium position, and its polarizability ellipse will be, let us suppose polarization will be in this direction. We have already seen that the polarizability is more, the ellipse is small. It will determine the magnitude because it is inversely proportional. This is the polarizability. It is the equilibrium value. Now whenever the molecule makes a symmetric stretching, just remember it. What will happen? This is C, this will move away, this oxygen will move away. Both are moving away. For polarizability, what you need? Separation of the charges. So that means the more the separation is, the more will be the polarizability, because when the electrons are close to the nucleus, then the polarizability will be less because it will hold those electrons tightly towards itself. It is not easy for them to move away. At that time, the polarizability will be less. But as the charged positive and negative charge centers move apart, they are free. They can be easily polarized. So when they move, stretch apart, when they are moving apart, the polarizability will be large because they are free now. They can be easily polarized now. And the polarizability ellipse will be small as compared to this equilibrium value. So it is in the bond axis here. What happens if you have displacement here? This is here stretching, this is here when they are coming close to each other. This is increase in distance, this is decrease here. This represents when you have C, this is O, this is O, this is C, this is O, this is O. Plus means that. Negative means you are decreasing the distance between the positive and the negative center. And at equilibrium, this is the equilibrium value. Here it is the equilibrium 0 when you are not stretching it. This is the equilibrium. This. At this, it has some polarizability. This is alpha here. Polarizability. It has some alpha. Suppose that it has this value of polarizability at 0 stretching when we are not making any displacement. Now, when we increase its distance, this, what will happen to polarizability? Increase?
It will be more.
It will be more. When we decrease its polarizability, this distance, this, it will go negative. This. And this polarizability is the equilibrium value, alpha naught or A naught or alpha naught, whatever you would like to represent it. Okay, now this was the case for the new one vibrational mode, that is a symmetric stretching. What about the bending? Let us take the bending, carbon dioxide. Sorry, we don't need this first. This is carbon. This is bending mode. This is its equilibrium. This. First draw the equilibrium. I made a mistake. I don't need to draw it first. First draw the equilibrium. Then give the excitation and it will bend. So this, it will bend like this. We know that here. Let it be. This is the polarizability ellipse here. The bending will first like this here, and this is here. Now, as compared to this, these O's are coming close to C here like this. Okay, sorry, they are moving apart, not coming close. They are moving apart. So when they are moving apart, the polarizability ellipse will be small, and we have this is again alpha, this is plus, this is minus. And remember that in this case, in bending mode, actually, there's not so much change in the distance, bond axis. There's not an appreciable change. There's a change, but very small. So it does not affect actually. So this is 0. This is your alpha naught or A naught here, and it will have like this. And it will go like this. Whether it goes down means negative, up means positive. Here, this is down, this is up, this is down. So when the molecule bends, then oxygen molecules bend upwards with respect to C, we will take it to positive Z here, zeta. When they are Bending downwards, it will be termed as negative. Just representation. It is for representation. Okay. So in this case, then the polarizability ellipse will be bit smaller than this. Now they are coming close to actually see here. So polarizability ellipse will be a little smaller, and it will be a bit circular rather than the ellipsoid, because now you have oxygen here, C here, rather than this linear configuration. So you apply field like this, you will have polarizability in this direction as well, in upward direction and in this direction. So it will be a bit circular. So we will draw it like this. And similarly, when there is a downward, the magnitude will be same shape. This will be the graphite. The last one, when there is asymmetric, first draw the equilibrium value position. This is the equilibrium, 0 minus zeta. Now see, for equilibrium, we already know this is the polarizability ellipse. Now asymmetric stretching, this is C, this is O. When this oxygen moves apart, it will be negative. When this oxygen moves apart, it will be positive. Left, right. Now what will happen? This O comes close. There will be low polarizability along the bond axis now as compared to this equilibrium value. This. Okay, the polarizability ellipse will be large as compared to the initial value. So it will decrease actually. This is the displacement here. This is some equilibrium value. So it will decrease actually on this side as well as on this side. So here, this is C, O. These two will give the same. So this is how we draw the polarizability ellipse when we apply some external radiation such that the molecule has a vibrational energies, vibrational transitions. The conclusion which we can draw from here is that, because we already know that the polarizability changes must for the Raman spectra. So you can be asked which mode is Raman active and which mode is Raman inactive. Only that mode will be Raman active where there will be a polarizability change. And those modes where there is no polarizability change, there will be Raman inactive. If you see here, the change in the polarizability in this case here is large because the bond axis change, the size of the molecule change here. In this case, there is not an appreciable change here. I will remove this. Sorry. Yeah, here it is. So in this case, as well as in this case, both the cases, the change is not so large. The molecule does not have a large change in the, because if, see here in this case, if this goes in, this will go out, or this will remain same. This go in, this will go out. The overall change in the shape is very small. So the polarizability d alpha by displacement is equal to 0 almost. So for small displacements, when there is a change in the polarizability, that is Raman active. And if there is no change, then it is Raman inactive. And this is all for today.